In 1977, NASA launched a pair of spacecraft that would become pioneers of the cosmos, Voyager 1 and Voyager 2. These twin probes were crafted not just as machines, but as explorers carrying humanity's ambition to the edge of the unknown. Their mission? To journey through the outer solar system and eventually escape into interstellar space, uncharted territory no human-made object had ever ventured into. Equipped with state-of-the-art instruments for their time, these spacecraft were designed to capture data and images that would reshape our understanding of the solar system. The Voyager twins embarked on what scientists called the Grand Tour, a rare planetary alignment that allowed them to visit the outer planets using gravity assists to slingshot from one planet to the next. This opportunity comes only once every 176 years, and NASA seized the moment. Voyager 1 and Voyager 2 were each assigned specific targets, ensuring a complete reconnaissance of the giant planets, Jupiter, Saturn, Uranus, and Neptune. Voyager 1 began its journey past Jupiter, delivering stunning images of its churning atmosphere and revealing the complexity of its Great Red Spot, a centuries-old storm larger than Earth. But perhaps the most astonishing revelation was the discovery of volcanic activity on Io, one of Jupiter's moons. This was the first time active volcanoes had been seen beyond Earth, challenging scientists' expectations of what celestial bodies could harbor dynamic geology. Next came Saturn, the ringed giant. Voyager 1 unveiled unprecedented detail in its atmosphere, magnetosphere, and its moons. But the showstopper was Saturn's rings. Once believed to be simple, concentric circles, Voyager revealed they were intricate systems of braided bands, gaps, and tiny moons embedded within the structure. These observations revolutionized our understanding of ring dynamics. Meanwhile, Voyager 2, which launched a few weeks before its twin, followed a slightly different trajectory. After its own encounters with Jupiter and Saturn, it continued onward, becoming the only spacecraft in history to visit Uranus and Neptune. In 1986, it arrived at Uranus, a pale blue ice giant tipped on its side, its rotational axis nearly parallel to the plane of the solar system. This bizarre tilt results in extreme seasonal changes unlike any other planet. Voyager 2 discovered 10 new moons, 2 additional rings, and unexpected features like a magnetic field tilted sharply off-center. 3 years later, Voyager 2 reached its final planetary destination, Neptune. Here, it observed the fastest winds in the solar system, reaching speeds of over 1,200 miles per hour, ripping through the planet's deep blue atmosphere. The spacecraft also delivered detailed data on Triton, Neptune's largest moon. Triton exhibited signs of cryovolcanism, with geysers erupting nitrogen gas, a clear indication of internal activity in a world far from the Sun. This moon also hinted at the possibility of a subsurface ocean, prompting questions about its potential for harboring life in the distant reaches of our solar system. These flybys didn't just bring back images. They told stories of diversity, violence, and beauty that were once inconceivable. The Voyagers helped reshape our understanding of planetary systems, magnetic fields, atmospheres, and the potential habitability of alien worlds. They didn't just visit planets, they uncovered worlds. In 1990, long after their last planetary encounters, Voyager 1 turned its camera backward at the request of astronomer Carl Sagan and captured one of the most iconic images in human history, the pale blue dot. Taken from over 4 billion miles away, Earth appeared as a tiny pixel suspended in a shaft of sunlight. This image, as Sagan famously noted, underscored the fragility of our world and the shared destiny of everyone who lives on it. It was a cosmic perspective shift, a moment of profound humility and unity. As the years passed, both spacecraft continued their journeys toward the edge of the solar system. In 2012, Voyager 1 crossed a boundary known as the heliopause, where the influence of the Sun's solar wind ends and interstellar space begins, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018, becoming the second. In the vastness beyond the Sun's protective bubble, the Voyagers continued to function, recording data about the interstellar medium, the sparse mixture of gas, dust, and cosmic rays that fills the space between stars. Voyager 2's plasma wave instrument detected faint but persistent hums, plasma oscillations, offering new insight into this mysterious environment. These sounds weren't dramatic, but they were profound, revealing that space, once thought silent and empty, is alive with energy. Even today, more than 14 billion miles from Earth, Voyager 2 continues to communicate with NASA's Deep Space Network. Each signal it sends takes over 18 hours to arrive. The data it returns is precious, a stream of faint whispers from the edge of the solar system that require delicate decoding and immense patience. Every transmission is a triumph of engineering and perseverance. Keeping Voyager 2 operational is a delicate balancing act. The spacecraft runs on radioisotope thermoelectric generators, which slowly degrade over time. With each passing year, its available power dwindles. NASA engineers must make tough choices, shutting down instruments to preserve energy for the most critical systems. Each decision carries weight. Which scientific instruments remain active? Which ones must be silenced forever? These questions shape the final contributions of a mission that has already surpassed all expectations. Yet, Voyager is more than a scientific mission. It is also a time capsule. Both spacecraft carry the golden record, a 12-inch gold-plated copper disc containing greetings in 55 languages, selections of music from different cultures, images of life on Earth, and even the sound of a heartbeat. Curated by a team led by Carl Sagan, the record was meant to tell the story of humanity to any intelligent life that might one day find it. It is a message in a bottle cast into the cosmic ocean, one that could outlive our species, our civilization, and perhaps even our planet. Today, the legacy of the Voyager program continues to inspire. Scientists are now sending missions to icy moons like Europa and Enceladus, searching for liquid oceans beneath their frozen crusts. Worlds where life might exist in the dark. Space agencies are designing next-generation probes to visit the Kuiper Belt and beyond, all building upon the path Voyager laid. It showed us not only what the outer solar system looks like, but how to reach it, how to explore it, and why it matters. Voyager 2 reminds us that human curiosity is limitless. That even with technology less powerful than a modern calculator, we can achieve the impossible. It stands as a testament to ingenuity, courage, and the thirst for knowledge that defines us as a species. As Voyager 2 drifts farther into the cosmic abyss, its mission becomes more symbolic. It is a lonely traveler bearing the essence of Earth, voyaging toward the stars in silence. Its power may soon fade, and its instruments may fall silent. But its story, our story, will continue to echo in the minds of generations to come. From distant planets and magnetic fields to haunting plasma waves and a tiny dot in the darkness, Voyager 2 showed us more than just scientific data. It showed us who we are in the vast, unfathomable universe. This is Space Loop, where we explore the past, present, and future of space exploration. Subscribe and stay with us as we continue uncovering the mysteries of the cosmos.